Hello and welcome to my presentation. Let me go ahead and set this up real quick. Okay, so this is my presentation on phonetic partitioning. I have a demo at the end and I'm just gonna go through it as quickly as I can. So what is phonetic partitioning? Um, it's just a way that we slice a word in order to break it down into the simplest form and then use those tiny slices to compare to our tree structure and see that, hey, does the phonetic qualities match what we have inside our data set essentially? So we load up our data set and then we test and see if any of the inputs, it can be one input, it can be a whole word, whatever you want, if that one matches up to what we have. So how does it do this? It aligns pre-existing phonetic transcriptions to the actual audio signal that we have in memory. The whole point is to load stuff from memory that we have inside the data set. And it gets down to like the nit and grit. And sometimes that might be a drawback is it's a feature and a bug. It's a plus and a minus is that it goes so far in depth that it is able to perceive stuff that humans can't even perceive, you know? To its detriment is it pays too close attention, but also to its advantage is it pays close attention so it doesn't miss anything. So yeah, my favorite thing about it is it's simple and straightforward to compared to what else we have available out here. Um, Here's a sample of what that looks like is we essentially cut each part of the word up and then we test and see if those parts match up to what we have. Now, why do we need to do this? Well, the main driver behind this project was the fact that most audio transcription software that's available is either for directed speech or the ones that aren't and allow for indirect speech or indirect speech aren't that good. If you ever have the chance to check out CMU Sphinx, it's really good when you're like speaking to it directly and it can transcribe anything you say, but as soon as you ask it to do that from a file, man, the stuff that you get is so slow, first of all, it's insane. But mine works within the millisecond when it comes to a word, so it's pretty good. Um, yeah, so my hope was just to alleviate some of that and find something that, because most of the software available is either commercial or something, and you can't really use them without paying for their licenses. So I was like, hey, let me go and make my own, and whether or not I succeed, it doesn't matter as long as I try my best. So that's what this is really all about. So how does it work? First of all, we have to talk about linguistics. Now, each one of those slices that I showed you can fall into a category of either a vowel or a consonant. Consonants have very low frequencies, vowels have very high frequencies because there's a lot of energy. Like, for example, ah versus s. You hear the difference? It's very low energy compared to high energy. So you can tell that the ones that are shaded darker are more likely to have a lot more energy. Quickly, though, a cool or a feature that you have to look out for when it comes to linguistics, and the reason I'm showing you this is because of the formant values. Anywhere that there's a spike, that function we call a formant. Now, there's a certain amount of formants in each slice, but specifically, we only care about F1, F2, and F3. So if you pay real close attention to all of these formants, you'll know that they create some form of equation. Ideally, we would want to compare this equation. Let's say, for example, this a sound was our input, and we wanted to compare it against to all the others. So we would basically superimpose it on them and then check and see which one has the closest match, and that would be our letter. So once we find the sound that matches, then we go a depth further and find that, hey, what letters are associated with this sound? So that's really it. So again, formant values are the vectors that we use to compare between the input and the existing data. The darkest areas of the spectrogram are our formant peaks, and there's lots of signal processing ways to collect that information, but that's not the focus of this project. The focus of the project is what do you do when you actually get the values, right? So yeah, like I said, ideally we'd like to do that with the input frame based on the equation, but that would involve maybe finding derivatives and a derivative is only at a certain point. So the way I chose to do it was using mean summation, which is not the most accurate way, but it is a way to do it. So a little bit more about the mean summation. Basically, we're going to collect the three values of the vectors. So all those three, we're going to collect basically every highest point for each foreman. So for example, for foreman 3, we're going to collect every peak here, the darkest area, darkest area, darkest area, darkest area. We add them all up and we divide them by the total number of the darkest areas for that foreman. So let's say there's, and this is frequency and time, by the way. Let's say there are 20,000. That's just a hypothetical. It might not be 20,000. We don't know. But let's just say it's 20,000 going across. And the highest is around, let's say, 2,500. So 2,500 plus 2,500 plus 2,500, all the way up to the 2,000th, 2,500. And then we divide it by 2,000. And then we get a value. So that is our foreman 3. We do the same for foreman 2 and for foreman 1. And we do that also for our inputs. So as soon as we load up my program, what it does is it does that for all the existing sounds that we have. There's over 100 consonants and maybe like 11 vowels. We collect all of them and we put them into a tree structure. Each tree structure has an object called a speech object, and the speech object is the parent or the super of either a vowel, subvowel, consonant, or subconsonant. And essentially, the first depth of our tree is all going to be either consonants or vowels. And then the subs will be subconsonants or subvowels. Now, the subvowels are just letters that are associated with the sound, but the consonants and vowels are the sounds themselves. So that's how that works. Basically, we slice the input interval and compare each to the input of the data set that's inside of the tree. Initially, I wanted to do this with Euclidean distance because something you'll notice, and is a drawback of using the cosine similarity, is that vowels are best determined by F1, whereas consonants are best determined by F3. That's because, like I said, consonants work at a very low frequency, so the highest frequency would be F3. So they're easily determined by their F3, whereas because vowels have high energy, their F1 is their most potent and has the most energy and is very easily to determine. So that's the way I did it, and I had amazing success. It was very accurate, but I wasn't able to split the difference between a vowel and a consonant. So one way looking back that I could have done it is by computing the Euclidean distance between the formant ones of an input and the formant threes of the consonants, right? And then if the Euclidean distance between a consonant, let's say the smallest one, is bigger than that of a vowel, then we know that that input is a vowel, right? But I didn't end up going that way. I ended up going with something better because it encompasses everything. F2, we don't really care about. So let's get into that. Cosine similarity, basically finding the dot product over the two magnitudes, and we basically compute every single product between each vector. So each variable is going to be compared, each input variable is going to be compared with one of the data set's variables, right? So let's say, for example, we choose the sound Z, then we're going to compare it with all of the values that are either vowels or consonants, and at each point, we're going to take our F1 compared to that speech's F1. Take the F2 compared to that speech's F2, take the F3, compare that or multiply that, add them together and divide them by the magnitudes of both. And usually you end up with numbers that look like that. And you could do it either using the cosine similarity. I chose to do the cosine distance, which is just 1 minus the cosine similarity. Makes my life so much easier. So then I just look for the minimum. This is another representation of that. Essentially, we're comparing a vector of three variables, F1, F2, F3, over the existing data set. So this would be our input over here to the right, and this is the data set to the left. Essentially, what we're doing, right? We have three variables in our vector, and we compare them, and then we find the minimum, meaning the one that has this almost the same direction, and that one is what we're going to assume is our closest input. Yeah, again, it has a drawback that those are primarily determined by F1. But however, it's a more encompassing, it's an all-encompassing solution and it works okay, you know. There's still a lot of room for improvement, but this is my first time ever doing this, having known nothing about linguistics, so you know, I'm okay with that. Let's talk about the code next. So the implementation is very simple. I have a lot of code that has to do with setting up and making sure that the code actually works, but the code itself is only comprised of 4 or 5 um, files, Python files, as well as the CSV file, and that is pretty much the data set. So essentially, we have a harvest, which is this, and we're using the Pratt library because, again, there's no need to reinvent the wheel. Excuse me. Um, and basically, it does all the signal processing for us and just returns the F1, F2, and F3. And I mentioned in the report, in the research report, that if you wanted to do your own signal processing, you absolutely could. And I actually found a way through my research of doing it, which is very similar to image processing, which involves median filtering. And median filtering, essentially, what it does is it collects all the neighbors of a pixel within a frame. So let's say your frame is 3 by 3, and you have a 9 by 9 picture. So it would start at frame 00, compare that to all the neighbors surrounding it, find the median, I mean, collect all the values, put them in a list, find the median of that list, and then return that and set that pixel to that median. Now, the difference with this algorithm would be instead of the median, it would be the max. So we would collect the max and then set it there. That's how we would find the Foreman values, because Foreman values are essentially the highest levels of energy in a spectrogram. And a spectrogram is essentially the image representation of sound, right? But I didn't want to do all that. I just wanted to focus on the classification of once we actually get the data, because there's a lot of people that have already done stuff like this, including Pratt. There's no need to reinvent the wheel. But yeah, essentially collects the F1, F2, and F3 averages. Next up, we have the binary search tree. It doesn't even use a binary search tree. I just named it that way and never bothered to change it. But essentially, what this does is it collects all the CSV items and it basically assigns them to either a vowel or a consonant because all that data is inside the CSV, and it helps debug a lot easier. So basically, it puts all the nodes inside the memory ready for us to compare once we have an input. And for a great portion of the semester, what I did was I would just compare single vowel, single vowel, single vowel, single consonant, and make sure that those were lined up, and they were, right? So the next step, like I said, is to compare. So now we do the cosine similarity, which I talked about. We have now the binary, the tree. It's not actually a binary search tree. It's just a regular tree. We have the tree, and what we do is we take our input, whether it be from a word, which I'll talk about next, or just a single input, which I talked about before. And what we do is we compare the first depth of that tree to that input. So we collect its F1, F2, F3. We send that to the cosine similarity. We send the first node of the tree, that vector of F1, F2, F3, we send that to the cosine similarity. It finds the cosine similarity and says, hey, okay, this one has this distance. Okay, and then we do that for all the nodes in the tree compared to the input. We have a list now of all the distances, and then we sort them, get the minimum, and that is our closest sound. Then in the second batch, for the second depth, once we find that first one, we dive deeper. Now we look for the letters. Inside the letters, okay, which one is closest? And then that is our output. And then finally here, we slice the word. So if you say a word like easy, then we do that. So yeah, this is my output for the word easy, and that is the output for the word shame. Didn't actually put in I didn't actually harvest the letter M just yet, so that's why it didn't show, but it's kind of close. Shrey, it's kind of close to shame, and then easy is Ipneasy. It's close. It tried. So it's slightly more accurate, lightweight, and speed is on par with CMU Sphinx. And now I will show you the actual running. So this is for shame. It runs in like 0.05 milliseconds. And yeah, if I do now the word easy. So let's play the word easy right here. Uh, let's go inside words. So this is easy, right? So now if we take easy dot wave and we run it, it tries, okay? It gets the E and the Z and the other E. So it's very close. And then the next step would just be to do a sim spell and then collect the nearest word to that. But it all depends on the slice intervals because the higher the slice interval, the less words we actually, the less letters we collect. So yeah, and the minimum we can go to is about 30 milliseconds. So playing around with this, you get all sorts of different results because it results in slightly different intakes. But all in all, it's pretty accurate. Like it does get the correct letters, the correct sounds. It just needs just a little bit more training, and I wish I had more time. But yeah, that's essentially it. Thank you for watching.